Okay, everybody. So, hello. Let's start with the first part of the lecture. So, for the first part of this lecture, I'd like to discuss soft theorems, and I better share my screen to do it. So here we go. Share. So, I'd like to discuss soft theorems, but before we get there, maybe just a little bit of a reminder of the salient features of last lecture. So last time, what we discussed was constraints that came on the possible dynamics, interactions, and therefore theories that we can write down for massless theories, for massless particles of spin 1 and spin 2, which were entirely motivated from representation theory type arguments. And so the upshot of this work, which was essentially to try and find a field operator type consistent realization of massless spin 1 and spin 2 objects, well, what we found was that in the case of spin 1, so the helicity +1 and helicity -1 states, what we usually call the photon, well, in order to maintain Lorentz covariance and therefore to be able to actually construct Lorentz invariant objects, it was necessary to introduce a gauge redundancy. It was necessary to basically require that the field operator itself was equivalent to the field operator up to a shift that is parameterized by a simple scalar function, which we call lambda, so by a d mu of a scalar function lambda. And this is what we usually think of a gauge redundancy for a photon. Then using very similar type arguments, considering the field operator for the graviton, meaning a spin 2 object, so the +2 and the -2 helicity object, what we found was that essentially all that needed to be done was to add an index to what was the scalar parameter in the spin 1 case. And so this is what we called xi nu. And so the redundancy was now a shift by the derivative d mu on the parameter xi nu. And for symmetry reasons, what we actually find is the symmetric derivative. So d mu xi nu plus d nu xi mu. And we recognize this as being the linearized diffeomorphism redundancy that is familiar from more elementary treatments of gravity. So again, the group theory type treatment forced upon us, if we wanted to maintain Lorentz invariance, in fact, a gauge redundancy for spin 1 and a linearized diffeomorphism redundancy for spin 2. That's already a very powerful conclusion. So today, I would like to continue constraining, actually, just sort of from first principles, the possible type of objects, theories, interactions that we can write down for spin 1 and spin 2 in the massless case. However, I'm going to leave strictly the field of group theory, and I'm going to add something which is, in fact, the idea of how you define charge and mass in terms of dynamical processes. And I'm going to, well, use those definitions, those vertices and those kind of diagrams in order to learn something about how charge and how mass can possibly appear in theories, consistent theories of spin 1 and spin 2. So therefore, what we're going to look at is in particular low energy photons, right? Which basically are defined by this diagram here. So for example, we consider a process where there is a charged particle. So the solid line here corresponds to a charged particle, comes in. It emits a photon. So it has ingoing momentum p mu. It emits a photon of momentum q mu. And so the outgoing particle will have the momentum running through it, p mu minus q mu. And we characterize the emitted photon by its polarization state E plus or minus of Q. And so in the limit that the momentum goes to 0, Q mu goes to 0, this is what we call a soft photon. And Well, as I already indicated here, such processes we saw last time allow us a definition of charge. A definition of charge that actually coincides with the usual definition of charge from known theories like quantum electrodynamics or scalar electrodynamics that we know and love. Now, therefore, what we're going to study regarding such photon emission, soft photon emission processes actually is going to tell us something about charge, and what it is going to tell us about charge is, in fact, charge conservation, that the total ingoing charge has to be equal to the total outgoing charge. But of course, we'll get there. Similarly, we were able to, we defined the notion of, analogous notion of charge for a graviton. So there we consider the same kind of diagram, but the emitted object is actually a graviton that carries away momentum q mu. Of course, we will go to the soft limit. And the object that in inverted commas we would call charge for the graviton, what does it couple to? Well, it couples to energy momentum. So basically, this is like mass energy. And we will find, in fact, the very strong conclusion that we can actually derive a constraint on how does it couple to mass energy, and it has to couple in such a way that the equivalence principle is respected. And we will of course see precisely the mathematical manifestation of the equivalence principle from the point of view of graviton exchange. So that will be the goal. That's where we're working towards. But first, I'd like to start by going through the photon case. So we're going to be talking about soft theorems. And in particular, well, as I already said, charge conservation, and the equivalence principle. Okay, so well, so the idea is the idea that we're going to pursue is that S-matrix elements or amplitudes of photons or gravitons are sensitive to charge and mass, as we already discussed to some extent last time. So S-matrix elements or amplitudes, speaking of course, S-matrix elements or amplitudes involving soft photons and soft gravitons, are sensitive to charge and mass. And of course, one manifestation of this was something that we calculated last time in some detail, which was, for example, the Coulomb potential between two charged objects and the Newton potential between two objects that are characterized by having mass or energy. So that's a very physical way of seeing that charge and mass are somehow mediated by photon and graviton exchange. And so, okay, we will use certain soft processes precisely to constrain charge and mass couplings. And the basic, let's say, technical crucial point that we're going to pursue is the following. So we're going to start with some arbitrary process. So now, well, with some arbitrary process, right? So we have some outgoing particles, okay? These can be a bunch of charged particles or whatever you want, okay? But they're not necessarily photons or gravitons. They're just the particles that these couple to. And there's some scattering process, so some kind of S matrix element. And then, of course, we have the ingoing particles. So we've been referring to this here collectively as beta and the ingoing guys as alpha. And we denote this process by the S matrix element S beta alpha, which is parameterized by all the momenta, P1, and then there might be spin labels. And let's say the total number of such particles involved in this process is capital N. So we go up Pn sigma n. And this corresponds to some scattering process. All right. But the point is now, this is some scattering process, but we want to compare it to something that is extremely similar. So it's similar in that we basically have the same guys as before. We have some scattering process here, symbolized by this blob. Okay, we have the same ingoing guys. So the ingoing guys, okay, so let's see alpha, but we do have, in addition, the emission of some soft quantum, which can be either a photon in the first case of interest or a graviton. And we refer to the final state here as beta. So the final state now includes, in addition to everything else that it included in the first place, an additional soft quantum, okay? And well, we will see what the point of this is, of course, but for notational reasons, let me just say that I denote this, so this process versus the matrix S beta alpha plus or minus, where the plus or minus refers to the, say, polarization state of this final particle here, which depends on the same set of momenta and say spin labels. But in addition, it also depends on the photon or graviton momentum Q and its polarization state E plus or minus, okay? And so this is the same process, but with a photon or a graviton added. And well, because we've been talking about the S matrix now, in fact, it's also practical to just talk about, so just the amplitude, which is essentially the S matrix, but without the overall conserving delta function, momentum conserving delta function removed. So we use also the object m beta alpha, the amplitude, and we compare it just notation wise to m beta alpha plus or minus, which obviously depends on the same kind of arguments as I wrote there for the S matrix in both cases. Okay, so now let's get right to business. So let us recall something. Let us recall that Lorentz invariance required for the photon a certain shift that, well, will turn out to be useful. That's in some sense just a statement again of gauge invariance. So it required that this E plus or minus mu of Q was actually equivalent to E plus or minus mu of Q plus some arbitrary shift C times Q mu, proportional to this momentum Q. Okay, but if the processes should respect this invariance, okay, then of course this means the following equation. This means that the amplitude, so you know we've been writing some amplitude m. Well, we can put the indices. For a photon, we've written this as m mu epsilon mu beta alpha, and I think you put a star here, but of course the starred quantity also has the same shift, but sorry, I actually called it E, not epsilon. So in this context, it means that M mu, some general matrix element, let's forget about the labels alpha, beta, that's not necessary for this argument, so that this contracted into E mu plus C times Q mu, well, this has to give us the same answer as just the E mu plus minus before the shift, because after all, you see, we're requiring that this kind of shift has no effect on physical processes, and so therefore the amplitude must satisfy this equation. Okay, but it's obvious that this is just a statement of the Ward identity, so this is correct. This means that M mu, if I contract it into Q mu, better vanish. Okay, and this is the statement for J is equal to 1. For J is equal to 2 for the graviton, there is an analogous statement, which is M mu nu into Q nu has to vanish. And I invite you to check for yourselves that this is correct. And the argument is just a tiny little bit more involved, but it is essentially the same as the one that you just saw. Okay, so we have to impose these two Ward identities. All right, good. So, well, let me now go into more details regarding soft photons. Soft photons. So, of course, when I drew the process, the soft photon process earlier, I was a little bit cavalier because I just put it on a particular outgoing line. Maybe I will remind you of this. I just put it on this outgoing line. But actually, of course, all that we know is that we start from some given ingoing state alpha, and we go to an outgoing state beta with the photon added. But we certainly don't care about where the photon came from. Let's say whether it came from this outgoing line, or it could have come from this outgoing line, or this outgoing line. In fact, it could even have been emitted from an ingoing line, okay? Any of the ingoing lines. And as we will see, actually less relevantly, it could have also come from somewhere inside here in this process. Those kind of processes, actually, when it comes from inside the blob, they will not contribute the type of singular terms that we're going to establish now. So we can actually forget about those, but we'll establish it. But what we do need to do is we basically need to consider emission from each of the outgoing lines and each of the ingoing lines, and we, of course, sum over all of these possibilities. Okay, but so good. So what we have is we have essentially our outgoing guys like that. We have our blob, the scattering process. Okay, we have our ingoing lines. Okay, we have alpha. We have this beta, and we call the amplitude m beta alpha, which depends on the set of momenta and spin labels. Okay, which I write like this. And we qualitatively, okay, we compare this to, well, we have the same outgoing guys, but let's say we add one soft photon to this outgoing line. Okay, this is our new state, beta plus the photon. We have our blob, and we have the same ingoing state, alpha. Or, of course, we could have the case which, well, we have the same outgoing lines. We still have a beta plus photon, but we will, of course, draw the photon as coming from ingoing line. Okay, so now we have up, 1, 2, 3 of those, and we emit, let's say, the photon from here. This is our gamma, okay, and this is still our alpha. And well, we will see that these two kind of emissions, one from the ingoing line and one from the outgoing line, are extremely similar. They actually just differ in one sign, and we will collectively call those amplitudes beta alpha plus or minus, which depend on the pi, sigma I, and formally, of course, on the soft momentum q. So the dependence on what would be the analog of the sigma I for the photon is, of course, its polarization state, and so that's already denoted here in this. We're using the plus or minus. Okay. So as I said, the extra gamma plus or minus could be emitted from an inline or an outline. So emitted from in or out. So now let us write actually down an expression for the amplitude, the relation between the amplitude with the soft photon and the amplitude without the soft photon. So in the soft limit, and let's consider right now at first the emission from the outline. Well, we would like to obtain an expression for m beta alpha plus or minus, okay? And this will be equal to m beta alpha, so the amplitude without the emission, okay? I'll have a comment on this in just a second. But what we need to add is basically, well, we need to add one more propagator, because, so you see, we are now looking at this kind of process, okay? And so in order to get these S matrix elements or the amplitudes, we of course consider amputated diagrams, meaning we don't have propagators for the in and outgoing particles. But what happens here is that now this, what used to be just the outgoing line, has been chopped into two, and only this part is now really an outgoing line, whereas this guy is part of an internal line of the diagram. So we need to add the propagator factor for this guy. So what does that give? Well, in the simplest case, where we have a spinless particle, I will actually write that down in a second, okay? Well, okay, this has some normalization factor, minus I over 4 pi to the power 4. But now this propagator, 1 divided by P1 plus Q squared plus M1 squared. Well, let me write it and then say what all these terms mean. We have 2i, 2p to the 2 pi to the 4th normalization factor, then E1, the charge coupling, times P1 mu into E mu plus or minus of Q, and of course this would be starred. That's a catalog of labels. Okay, let me make some space to write the star. Right, so this guy here, complex conjugated. Okay, so the comments on the propagator that I promised. So first of all, so the outgoing momentum of this particle is P1 and its mass is M1, and we assumed that the emitting particle is spinless. Then you can ask yourself, well, what did the momentum on this line have to be before the emission so that it is still P1 after the emission? And the answer is obviously P1 plus Q. So that explains that factor here. The rest, this guy, that was just the photon emission vertex that we discussed at the beginning of this lecture, and of course in more detail last time. Okay. So then let me just say the last bit, which is that this guy, so this is the process which is exactly the m beta alpha amplitude without the soft photon, and that's because we're looking at the limit that q mu goes to 0. So since that is going to 0, the rest of the process is the same. And then the remark was that for simplicity, we assume that the emitting particle is spinless. Emitting particle is spinless. Scalar. Of course, we don't need a comma to assume this. Okay, so very good. So so that explains this expression here. The only difference to the emission from the inline is, by the way, related to the sign factor here, which will lead to an overall sign. And that again, you can just that you can just understand because of momentum conservation. Okay, but now let's look at this denominator. So what we have is a denominator. Okay, we have P1 plus Q all squared plus M1 squared. Oh, and I haven't bothered writing the epsilon factors because they really absolutely don't matter for the argument. So what we get is we get P1 squared plus M1 squared plus Q squared plus 2 P1 dot Q. And the important thing to realize is that P1 squared plus M1 squared is actually equal to 0. It's equal to 0 because the outgoing particle goes on shell, which means that P1 squared plus M1 squared is equal to 0. The same is actually true about the photon, so we can say that Q squared also is equal to 0. It's a null particle. So in fact, all that is left is the factor 2 P1 dot Q. And obviously, for every other possible line that it could have been emitted from, there is going to be an analogous term that contributes, which is something like Pn dot Q, n being the arbitrary label. So we can write the soft factor. So hence the soft factor, this is what one calls these kind of contributions, by the way, reads. Well, for the outline, we have m beta alpha plus or minus. This becomes m beta alpha times E1 P1 mu E mu star of Q divided by this denominator, which becomes 2 P1 dot Q. Now, of course, I should have said that we've cancelled this 4 pi to the 4th. This guy here, minus I times I is 1, and 2 divided by 2 is actually equal to 1. So this is what the soft factor becomes. So this is from the outline. And then because of momentum conservation, it works the other way around. You can convince yourself that m beta alpha plus or minus for a soft factor corresponding to an emission from the inline becomes m beta alpha, well, with a minus sign actually. So let me put the minus sign in front, times E1 P1 mu E mu star of Q divided by P1 dot Q. And that is from the inline. And notice that I'm calling the momenta both P1 here. Obviously, you just put whatever momentum label corresponds to the particle from which the emission happened. Okay, that's the point. All right, so these are our in and out soft factors. But all in all, what we should do is we should sum over all possible emissions. So all in all, since the emission can come from any line, can come from any line, well, m beta alpha plus or minus is then equal to m beta alpha, this factors out, times the sum over all in and out particles, where you have En, its charge, times Pn mu times Em mu star of Q, divided by Pn dot Q. And then crucially, because in emissions from in particles come with a minus sign, we need to put this sign factor eta n here, where eta n is equal to +1 for out and -1 for in. Okay. And then, excuse me, I should have said there's the contribution, which I call plus internal. So there could also be the emission from any of the internal lines which are hidden in the blob. However, those guys turn out to be irrelevant because they don't have no 1/q factors. They don't have these kind of factors 1/q, which actually turn out to be the singular type factors that we need to single out. And why don't they have these 1/q factors? Well, that's because it was crucial for the particle to go on shell in order to get the 1/q factor, because that's why everything else canceled out. And for the internal lines, they do not go on shell, and so there is no reason for this 1/q singular behavior. So that's why, as I actually already said earlier, you can only you get away by just looking at the factors, the sum over emission from all the in particles plus emission from all the out particles with that relative sign. But now we're getting somewhere, because now let us recall once more something we know about the amplitude. Well, we know that m beta alpha plus or minus is written as E mu star of Q m mu plus or minus beta alpha, except that now we know precisely what is m mu. We've written it here, right? We just need to isolate everything that's not E mu star. So it's just the rest here. Okay. And furthermore, this must vanish if I replace the polarization E mu or E mu star, if I replace this guy with the momentum Q mu. That was our Watt identity. So that gives us the following equation. It gives us 0 equal Q mu m mu plus or minus beta alpha, which is therefore equal to m calligraphic m beta alpha times the sum, n goes from 1 to capital N, of eta n En Pn dot Q divided by Pn dot Q, because I've just substituted Q mu for this guy, and so I have Pn dot Q, and in the denominator I've had Pn dot Q all along, and so those guys happily cancel out. And our conclusion is that, so this is the first main conclusion, 0 equal to sum n1 to n of eta n E n, which you can write in a more suggestive manner, That is saying that the sum of all ingoing charges, En, better be equal to the sum of all outgoing charges, En, right? Because they sum to 0 with this sign. So that's our statement, and this statement is nothing but global charge conservation. Okay, so very nice, in my opinion. We have been able to conclude simply from studying, well, requirements of Lorentz invariance, gauge redundancy, and the definition of charge using the emission of a soft quantum, something that gave us what I believe is an extremely strong constraint, namely that charge needs to be conserved for all consistent theories that we can construct using those criteria. Now, let's go in detail through the case for the graviton, because this will be technically extremely similar. You won't find anything that surprises you, but the conclusion, at least in my opinion, I think is even deeper. And the reason why the conclusion is even deeper is simply the presence of the additional index. But the presence of the additional index actually makes this constraint, this analogous constraint, deeper in my opinion. So I will now move on to soft gravitons. Soft gravitons. Okay, so now we're going to look at our process where we have some scattering of in states into out states, but what we do is we add, surprise, surprise, a soft graviton in the out state. So let's emit it from here, and this is some soft graviton. So we're interested in m beta alpha versus m beta alpha plus or minus, and to be completely explicit, we can put a 2 here because it's an helicity plus or minus 2 quantum that we consider. Now, I can actually skip all of those details that we went through right now and just say by the same reasoning as above, one obtains actually that this amplitude m beta alpha plus or minus 2 is equal to m beta alpha without the soft graviton times our friend eta n times not En but Gn, the gravitational coupling. Okay, I'm summing over all in and out particles. And now see, it's just the numerator which is modified. It gets this extra momentum factor. I'm sure you remember this, but we always had 2 of these, and that of course was necessary because we needed to saturate 2 indices in the polarization tensor. However, nothing changes about the denominator. Okay, even though this is probably obvious to you, but let me just emphasize again, the denominator, this just comes from the fact that I'm splitting, let's say, this outgoing line in 2, which is a property of this solid line particle, so the particle that couples to gravity. And so I add just 1 propagator factor for this guy here, and that's exactly the same propagator factor as I would have added for the photon. And the only difference is here in the numerator, which is that we have 2 momentum factors, as we did already in our more fundamental treatment last time when we defined mass through the emission of a soft graviton. So then, of course, you also would have the internal contributions, but as we said, we can forget about them. Now, let's go through the same steps. So by Lorentz invariance, okay, by Lorentz, we must have that m mu nu plus or minus beta alpha must be, if I contract it into the momentum q, say on the new line, this better vanish. And again, the expression for m mu nu is defined already thanks to the soft factor. So the equation that we get is 0 equals m beta alpha sum over little n up to 1 up to capital N eta n gn. But now notice that I contract the momentum. Oh, yes, so I had a typo here. This is p mu p nu. So I contract the momentum q nu into this p mu, so I get the factor p dot q, which cancels, but I'm left with one factor of the momentum here. That's crucial. So I'm left with pn mu. And therefore, the constraint that we get for the helicity 2 case is 0 equals sum n1 up to capital N eta n gn pn mu, which is slightly more complicated than what we got for the photon case. And the conclusion will therefore be dramatically altered. So what is going to be the conclusion? Well, we should remind ourselves of one thing we know. We already know that momentum is conserved. We know that the sum of eta n pn mu is equal to 0, because that's just momentum conservation. Sum of outgoing momenta is equal to sum of ingoing momenta, and that's ensured in this by this eta factor. So now, if you stare at the constraint that we had, if you stare at this constraint here, okay, then the only sensible way of solving it, I will return to why I call it sensible. The only way of solving it is actually, so the conclusion, oops, this moved. The conclusion is that actually gn has to be equal to 1 and the same g for all n. Reason being that if that is the case, then the constraint just translates into momentum conservation, which we know to be true. So sum over ingoing momenta is equal to sum over outgoing momenta, and this is the conclusion. So, okay, look, the reason why this is the case, of course, oh no, let me return to that. The point being that now that simple constraint that led to charge conservation in the photon case leads to the fact that every possible particle that can couple to the graviton must couple with the same strength. Okay, and that's of course another way of saying that it must obey the equivalence principle. Okay, if you want, we have just derived the equivalence principle. And to me, that's the totally amazing conclusion, right? So the conclusion for the spin 2 case is that the graviton must couple with the same strength to every possible matter particle that you could add. The equivalence principle. Okay, so I just want to add a couple more minutes to go back to why this is actually the only sensible conclusion. Well, the point is, like, imagine you wanted to impose instead just the full constraint. So let's just do the same as we did in electromagnetism. So we have eta n gn, but then we have pn mu is equal to 0. Well, the point is, we know that momentum is conserved. Momentum is always conserved. That's imposed, for example, by this momentum conserving delta function. It just momentum is conserved, no argument. So we know this is true. So what does it mean if I impose both of these constraints at the same time, momentum conservation and this? Well, it means that only scattering processes are allowed which conserve the momentum and which have another linear relation among momenta, which means that only very special kinematic configurations are actually allowed for scattering involving gravitons. The graviton emission means that even for the matter particles, only very kinematically special configurations are allowed. And that, of course, makes absolutely no sense. I mean, just think about the implications this would have for particle physics, which are absolutely not what we observe. So this makes no sense. Okay, this is why I said the sensible conclusion is this one, the equivalence principle. And the final remark that I want to make is that we only looked at scalar external particles, only looked at scalar external particles. But in fact, the analysis for spinful particles reaches the same conclusion. So analysis with spin is actually considerably more complicated. So I didn't want to go into the details for pedagogical reasons, because conceptually it reaches, is more complicated, but it reaches the same conclusion. Which of course is important, right? I mean, so this means that the coupling can also not depend on the spin of the particle. Important point about the equivalence principle. Just because you have an electron doesn't mean it is allowed to be coupled in a different way than the Higgs boson. Okay, so I'm already a couple of minutes over time, so I will conclude here, and I will see you for the second half of this lecture. Bye-bye. Okay, so I think it's time to start again. So let me arrange my windows here. Okay, excellent. Welcome back, everybody. Yes, Adrian.
I just have a question about what you did in the last part of the previous lecture. Shall I go on with the question? Okay.
Sure. Why not? Yeah.
Okay. So it's about the sub-theorem for the photons. So I don't see in the derivation of it, I don't see why it doesn't lead to an equivalence principle in the same way as in spin 2.
Why?
Because we seem to reach the conclusion that some linear combination involved in the momenta is equal to 0, and there we also know that the momenta are conserved. So why don't we conclude from there that also the charges are the same?
We don't. I don't see what linear combination you speak of.
Maybe I didn't copy it right.
So there is just no, we don't. And I don't want to change documents now, but the point is that there's only one factor of the momentum in the numerator and one in the denominator. So
and it cancels out. Yes.
Yes, right?
Yeah. I didn't copy it right indeed. Yeah.
Okay. Good. So good. So you're still raising your hand.
Pardon?
Done? Okay. Good. So now that was actually quite fun. I like the soft theorems and the conclusions that you get from them. And so we're going to move on to something that is also very fun, but it's different tack. So far we've had constraints that are sort of on the dynamics and so on. Now we're going to go on a constraint on the possible spectrum of theories, and this is something that goes under the name of the Weinberg-Witten theorem. So we have all of the tools now at our disposal this is a slightly different argument. So it's slightly change of tack now, but it will be easy for us to understand it because we have everything in place that we need. So the Weinberg-Witten theorem.
You're not screen sharing.
Oh, well, that's indeed. Thank you. Yes, do remind me of such things, and if I forget to record and things like this, that's really helpful. I don't know what's. Okay. Fantastic. So we will discuss. So this will be a discussion on constraints on massless spin and one particles, or the existence of such particles. Okay, constraints. On the well, the occurrence in the spectrum of massless spin 1 and spin well, spin 1, 2, and actually up higher spin particles. And so the main physical point that will also be important for us in the latter part of this course is that this actually is often used to rule out certain the notion of emergent gravity, or certain notions of emergent gravitons. And we will be more precise at the end of this lecture in what how it works, if it works, and in what circumstances it doesn't work. So I will start by giving you the statement, and then we will go through the argument. So the statement is that, okay, there is two versions of it that I'd like to discuss again both. One of them is one that talks only about photons, so the spin 1 case, and then the other one that talks about the spin 2 case. So A is for the photons, and it says that a theory containing a Poincaré covariant J mu, so a conserved spin 1 current, forbids massless charged particles of spin J strictly greater than 1/2. So let me write it. So a theory containing a Poincaré covariant J mu, so something with one index, forbids massless charged particles of J strictly greater than 1/2. And of course, we mean that the current should also be covariant, should be conserved, excuse me. So expectation value of the current, d mu, is equal to 0. Now B, the one that, again, in some sense, in its conclusion is more interesting for us. I'll state it that a theory containing a Poincaré covariant T mu nu forbids now massless particles which are charged under T mu nu of spin J strictly greater than 1. Sorry, by the way, let me look at the participant window again so I can see if people are raising their hands. Let me just arrange it. Okay, good. So I will write it. Okay, so a theory with a Poincaré covariant conserved. I didn't write the word conserved above, but that's of course what I meant by this, okay? Conserved T mu nu, so now we add one index, okay? Forbids massless charged in inverted commas particles of J strictly greater than 1. And of course, the conservation again is d mu T mu nu is equal to 0. And charged in inverted commas, you already understand it because we spent some time on this, is basically has a non-zero charge. So charge is a non-zero, is a non-zero T0 nu d3x, right? So this is like mass or energy, if you want, energy current. Right here, what you have is, of course, you have a non-zero J0 d3x. That's electric charge, right? Good. So in particular, I mean, just to go back to this second point here, we can say, okay, there is, e.g., there is no composite graviton from a Lorentz invariant or Poincaré invariant substrate. What do I mean by this? I mean that, let's say we have this great idea that the graviton is actually a composite thing, but of course we know what the graviton is. It doesn't matter if it's composite or not. It's going to be a massless spin 2 particle, okay? And so you cannot have a momentum, non-zero momentum current carrying spin 2 massless object if you start with a theory that is itself Poincaré covariant and has a conserved energy momentum tensor. So that just won't work. It's ruled out by the arguments that we will give now. But again, we'll come to a more detailed, slightly more detailed discussion of this in due course. So before getting to a more qualitative discussion or possible implications or possible loopholes, let's go over the argument in some detail. So I'll start by giving you the overall idea of the proof. And then we will go through the individual items one by one. So let's look at matrix elements of the following form. Let's look at some momentum P primed with plus or minus polarization, so it could be a photon or a graviton. And let's look at matrix elements of either the J mu or the T mu nu. And P plus or minus H, okay? So these are the kind of states that we constructed, of course, the unitary irreps of helicity plus 1 minus 1 and plus 2 minus 2. And then we will look at this and we will pursue two different lines of argument. We pursue the line of, sorry, is this now again? Good. Yeah. We pursue the line of argument that via Poincaré covariance or Lorentz covariance and via and what we define to be the charges, okay, we will give a very general argument that those kind of matrix elements have to be generically non-zero. But then we look at a different line of argument in which we still look at the same kind of matrix elements, but now we argue via the Lorentz or Poincaré transformation of the states themselves, so P plus or minus H, okay, that these guys have to be 0 If in the J mu case, actually maybe I'll give this a color so that that'll be easier to make the connection. Let's make J mu blue. In the J mu case, this has to be 0 if J is greater than 1/2. And in the still black T mu nu case, this has to be 0 if J is greater than 1. Okay. And so this, of course, is a contradiction. That's not great, right? Because on the left-hand side, we say that they have to be non-zero. And on the right-hand side, we say that they have to be 0. So something has to give. And the thing that has to give is that to avoid this contradiction, so this is the upshot of the argument, to avoid a contradiction, one excludes, or one must exclude, these particles, the particles which cause the contradiction. Okay, so J greater than 1, and in blue J greater than 1/2, J greater than 1/2, massless and charged, you know, in the sense that we discussed, particles from the spectrum of a consistent theory. Okay, because then these theories do not contradict any of the deductions, any of the mathematical arguments that we're going to now illustrate. So that's a general idea. And so what I'm going to do is I'm going to start on the left-hand side. I'm going to give you the argument that these guys should be non-zero. And then I'm going to contradict myself by looking at the right-hand side and giving you this argument. And of course, the conclusion will be the one which we've already mentioned. Okay, so let's go into detail. In more detail. So this was basically the sketch. Let's go. And of course, as I've said so many times, we will start with the case of the photon, and then we will see what the general argument is. And then in order to go and treat the graviton, we just add one index, and we will find, well, in this case, actually, the argument, there's really not much, there's no more subtlety. And as you can see, the conclusion is just the same, except that you bump up the spin by half an increment. So what does it mean to carry charge? Well, one way of saying it, okay, we carry charge if we act with the charge operator onto a state P plus or minus H, and obviously I'm suppressing the label. There is this label, what is my charge, and I get Q P plus or minus H. Okay, so here Q now is really the charge, not some momentum 4 vector whose indices I'm suppressing. So in this section, actually, I'm making sure that momentum I always call P and P primed and things like that, because Q is reserved for charge. But we can also calculate charge. But we can also calculate charge as follows. Okay, so we can look at the matrix element P primed of this operator P prime P, and I'm obviously, just for notational simplicity, suppressing the helicity index here, and so that is equal to, well, we know, I've written it actually before, but we can write the charge operator as the integral over the 0 component of the current. So the current here is, of course, J0. So J0 is the 0 component of T and X, P, okay? And so now, just using the usual Heisenberg picture, we can write this as d3x p primed e to the I p dot x, the momentum operator, j0t, and then at the origin e to the minus I p dot x onto p. But now we act with the momentum operator giving us p primed, and to the right giving us p. Okay, so we can write this very simply as d3x e to the I p primed minus p dot x into the matrix element p primed j0 of t. I'm not going to write the x is equal to 0. P, okay? But we can do the x integral because nothing depends on x here, and this is just the definition of the delta function, okay? So putting in factors of pi, we get 2 pi cubed the 3D delta function p primed minus p times the matrix element p primed j0p, getting more and more sparse in my notation on the j0, but of course the arguments are implied by the line before. So evidently, okay, we conclude from this that in the limit that the p primed approaches p, the matrix element p primed j0p is equal to q, the charge, over 2 pi cubed. And why is that? Well, because we compare, right? We compare this notion of charge, this is very elementary one, which of course gives us little q times the delta, with this definition of the charge. Okay, good. So now we use Poincaré covariance. Okay, so then by Poincaré covariance, this statement just has to be true in a general frame, and so the statement that we find is that the limit p primed approaching p of the matrix element p primed j mu p has to be equal to q mu over e times 2 pi cubed. Okay. Oops, sorry. Let me try and draw the box again. Okay, excellent. So, yes, Aranaba, 1 second. I actually see that you're raising your hand. So we have the point is that we've also used the conserved current, because for a conserved current, it's basically the Noether theorem that tells us that the zero component gives us the conserved charge. So we've also used conservation. And we've used Lorentz covariance by covariantizing this expression. And of course, the covariant expression, sorry, what am I? This is embarrassing. This is, of course, q times p mu. Maybe this was Aranaba's point. Okay, because q was the charge. I insisted on the fact that q was not a Lorentz vector. And if you take the zero component of this, you see that p mu, p0 is e, so I basically recover precisely this. And in a general frame, this is the expression. Yes, but now Aranaba, please.
Yeah, I missed a point, like what happened to the delta function? In that,
well, that's why I'm only considering in the limit that p prime goes to p.
I see.
Yeah. Okay, so so note, I just want to say that note implicitly we need conservation here for this argument. J mu. Good. I'm glad I caught myself there with the Q mu, and so it's Q P mu over E 2 pi cubed. Excellent. Now, good. So, oh, and of course, this guy we know is non-zero. Okay, generically, this is non-zero. Just because we have the explicit expression, okay, we know that it's non-zero. So we have said something now about these matrix elements, J mu, that tells us that they should be non-vanishing and totally independent of what the helicity was, right? I mean, I suppressed the helicity index here, but I think you agree that I could have just carried it through. Pranjal.
Sorry, I missed the point where we used the conservation of J mu.
So I think you need the conservation of J mu simply, otherwise you wouldn't have the charge defined as the integral over the zero component. I mean, this is all tied into the, Noether theorem.
Okay, and I also missed what this factor of capital E was, sorry.
It's because if you go to the zero component of this, you want that the zero component recover this expression.
Okay.
But the zero component of P is called E.
Okay.
So then you have P0 over E, which is 1. And so you get this.
Thank you.
Yep. Okay. Thanks for the question. Good. So now let us go to a special frame. Pranjal, you still have your hand raised. Okay, good. So now, now I would like to argue the other side of this argument, which was we've used, as I said, conservation of J, Lorentz covariance, and the definition of charges to argue that these matrix elements are non-zero. Now let's look at the right-hand side of this argument, where we find a seemingly different conclusion. So in order to do this, it's actually very opportune to go into a special Lorentz frame. So let's go to a special Lorentz frame. We, of course, allowed to do it because we think that our physics should be Lorentz covariant. So let's note P and P primed are both null. Okay. So what we find as well, if we look at P prime plus P all squared, that of course becomes 2 P dot P prime, because P prime squared and P squared are just 0. And this we can write, because they are null vectors, we can write it as 2 times the length of P 3 momentum part and the length of P prime 3 momentum part times the angle between them, cosine phi minus 1. Okay, because remember, this is just zero component minus the inner product of the spatial components. The inner product of the spatial components is the lengths of these two times the cosine between them, right? I'm sorry, I can just write it. Okay. This is 2 P dot P primed, this 3 component product, which I can write as the length times the angle between them, minus, and then of course, because they're null vectors, their zero components are just the length of the 3 components. Okay, so I obtain indeed just this expression here. Simple. Okay, now where I've defined, I've defined that this angle phi is the angle between the 2 momenta. So we have, I don't know, P primed, P, between them we have phi. Good. So what that means is, okay, that P prime plus P itself is time-like, except in the special case that phi, except for phi is equal to 0. So we will now proceed by saying, let's look at phi non-zero. So one can actually directly do the phi is equal to 0 analysis as well, and it won't change our conclusion. I don't want to go through it, but another way of saying it is that it would be crazy if we had to change our conclusions for just one kinematic configuration. So because, right, we're currently in the business of making statements about consistent theories, it would be crazy to come to the conclusion that a theory is consistent only if all momenta are collinear. Okay, so but you can actually also do the phi is equal to 0 analysis separately and you come to the same conclusion. But I think it's, you agree with me that it's more than reasonable to focus right now on the case where the momenta are not aligned. In that case, the conclusion is that the sum of the four momenta is time-like. Okay, so the sum of the four momenta, even though we have two massless particles, okay, the sum of the four momenta is as if it were the four momentum of a massive particle. And what can you do for a massive particle? You can go to the rest frame. Okay, so we can choose, this is now our frame, can choose a frame, okay, such that p prime plus p mu is equal to just, there's just the 0 component, okay? And then there's spatial momentum 0, which of course means that the momenta in this frame are back-to-back. Their sum is exactly 0, so the momenta have to be precisely back-to-back. Okay, so what we really have is that we can write p prime mu is equal to p minus p mu, where of course p mu is equal to p absolute value plus p mu, okay? Right, because the sum of the spatial momenta gives 0, and well, there's just some energy here. So in this frame, we have p primed p. And so why is this actually a nice frame? Well, you notice already just immediately, intuitively, there's a lot of symmetry. There's axial symmetry in this frame. And we're going to exploit this axial symmetry by actually looking at Lorentz transformations now, which do rotations around this axis. Oh, I think I'm calling it theta, the angle around this axis of the momentum. And what is nice about this rotation is that it leaves the momenta invariant, right? Because the momenta, both, doesn't matter whether they're plus or minus. If I turn around this axis, I don't change the momentum. So let's do that, okay? So what we do is we go and we have the states which undergo Lorentz transformations. We have that u, well, in general, u of lambda p prime plus or minus h, they go to, well, our normalization factor, e to the plus or minus I times some angle theta that was determined by lambda and the reference, the momentum p, times its helicity lambda p primed plus or minus h. And I have u of lambda p plus or minus h, which is m e to the plus or minus I theta. By the way, I'm not writing theta in red. This is not yet the same theta, but I'm going to argue in a sec that it is. Lambda p plus or minus h. So this was our thing where, you know, in general, we used the definition of the little group element to find what is the actual Lorentz transformation. In this case, what is the actual angle, oops, that appears here, what is the actual angle that appears here given our induced representation technology. But in this particular frame, it's super simple because the Lorentz transformation is if I choose the Lorentz transformation to be a rotation around the momentum, nothing happens to the momentum. So what I have is for a rotation by an angle, I called it phi, I apologize. I called it phi here, I guess because I wasn't using colors before. Okay, so by an angle phi around P, okay, around the direction defined by the momentum P, we have what? Well, we simply have that theta of lambda P is equal to, well, this one I call phi. And the only difference is that theta lambda of P prime, because P prime, the spatial momentum is in the opposite direction, so the sense of rotation is inverse, minus P. Okay? And thus, the Lorentz transformations, this is the important bit now, okay? They are equal to, so this guy goes to e to the minus plus I phi h p primed plus or minus h, and p plus or minus h goes to, well, all that happens is that you reverse the sign here in the exponent, okay? The sign being precisely this. Okay, so now we're off. So what happens is so now let's look at the matrix element again. Basically, Poincaré or Lorentz covariance is the statement that, remember the U transformation, U J mu U inverse, right? We have something like U J mu, well, U inverse J mu U, okay, should be equal to something like lambda of our angle phi mu nu J nu, okay? That's something that way back we already derived. So let's do that for the matrix element. Well, if we do this inside the matrix element, okay, so what's the matrix element? Let me just remind you. This matrix element, okay, then of course I can act U inverse J mu U. I act with the U onto the P primed and onto the P. That's just the thing that we figured out, right? We just figured out how does U act on P primed. Gives us this. So that means that E to the plus or minus 2I phi H P primed plus or minus H J mu P plus or minus H, that must be equal to, well, must be equal to this guy inside the matrix element, because I'm just using our Lorentz transformation properties. So lambda I can pull out, mu nu, but it's equal to this acting on P primed plus or minus H J nu P plus or minus H. And in particular also, of course, this Lorentz transformation here has to be the rotation by phi around P. Okay, which is the rotation by minus phi around minus P. Okay, so this statement that we have here, it is really nothing but a statement of consistency Lorentz covariance. Okay, so this must be true if the theory is Lorentz covariant. That's in some sense a very simple requirement. But now what it is, it's basically an eigenvalue equation, right? What this is saying is that the matrix lambda, the matrix lambda acting on the vector, this is a vector index nu, okay, is equal to the vector with the potential eigenvalues, which are governed by, well, the sign here, but they're also governed by the helicity. And so now we can actually see if we can solve that eigenvalue equation, okay? So it's a simple eigenvalue problem. The eigenvalue problem is the following. Let's see, for example, a P is in the Z direction. Why not? Okay, we just choose our coordinate system in the way that we like it. We have something of the kind that say, what does this Lorentz matrix look like? Well, it's like a cosine phi minus sine phi nothing, sine phi, cosine phi nothing, 0, 0, 1. Okay, and I have the, so this is the Lorentz transformation, doesn't act on the 0 component, and here I have my rotation matrix, and of course these guys are 0. Okay, acting on something like J0, J1, J2, J3. By something like, I mean, of course, I mean it inside the matrix element, but indulge me. Lambda J0, J1, J2, J3. Okay, what can we get? Well, of course, you can solve this, right? This is really like right in front of you. It's an eigenvalue equation. So we find that lambda is, the following eigenvalues are allowed. 1, e to the plus or minus I phi, and that's it. Okay, and this has to be equal according to our analysis. It has to be equal to what? It has to be equal to e to the, let's make sure I get the signs right, plus or minus 2I phi h, right? This guy here. It's our equation. So e to the plus or minus 2I phi h. So how can we solve it? Well, obviously we can have either h is equal to 0. We can just write it. H is equal to 0. That gives me the eigenvalue 1. Or we can have h is equal to 1/2, which gives me the eigenvalues plus or minus 1. But it's not consistent for any other h. So for any other h, for all h that is greater than 1/2, well, the only way that this equation can be correct is if the matrix element itself is equal to 0, right? So for all h greater than 1/2, the matrix element p primed plus or minus h j mu p plus or minus h is equal to 0. Okay. So of course this also is true in the limit p prime goes to p. So we have established part A of Weinberg-Witten. What do I mean? Well, we precisely are in the situation that I outlined. We argued that this has to be non-zero no matter what h is, but just now we showed that it had to be just by consistency of Lorentz covariance, that it had to be 0, this matrix element, for any j greater than 1/2, because we're in the blue spin 1 case. So the only way to go around this is by just saying that in a consistent theory that satisfies our requirements, no particles that are massless and charged and that have spin j greater than 1 can exist. Okay, that's part A of the Weinberg-Witten theorem. So maybe I will take another 5 minutes, so no, 7 minutes from now, to also talk about the Graviton case, because I'd just like to get that written down. It's really not more complicated than what we've done now. Okay, so let me do this. So here, of course, what we look at is we look at p primed t mu nu p, and we look at the corresponding charge, which is the zero component of t mu nu, so t0 nu. But t0 nu, of course, is also known as p nu. Okay, so we look at these things. So what we have is we have, because of the same kind of arguments, we have that p primed, I'm suppressing again the helicity labels, okay? That is, of course, equal to the momentum eigenvalue p mu times the delta function, okay? But I can also look at our friend, so we have this, and also we do the same story where we look at the matrix element p primed p mu p as being the integral d3x of p primed t0 mu of tx. Oh dear, sorry, I can shift this, it's fine. Okay, I look at this, right, p, okay, and then I use Heisenberg evolution to write this in terms of the t mu at the origin, and then I get my delta function as before. So I get 2 pi cubed delta 3 p prime minus p times the matrix element p primed t0 mu p. Sorry, this is really smushed here. I can do a little bit better. All right, so I can squash this together a bit. Okay, so p primed t0 mu p. It's exactly the same argument as we did before, except previously we had J0 there, which was the charge Q, and now we have T0 mu, which is the charge P mu, if you want the charge corresponding to energy / mass. And so our conclusion is now that we have the limit that P primed approaches P of P primed T0 mu P, this is now equal to P mu over 2 pi cubed. And here this is correct now. This is the vector, because remember we actually said several times that Q is the charge for a charged particle in the sense of electromagnetism, but P mu is the charge for a charged particle in the sense of gravity. Gravity reacts to mass energy. And that is actually a Lorentz vector. So by Lorentz covariance, we find in this case, there's going to be another index, as I always promise. We actually have P primed T mu nu. Okay, this is the covariantized version now. I covariantize this index, P. That now has to be equal to P mu, P nu, and then with the same factor here, E times 2 pi cubed, for precisely the same reason as Pranjal was asking before. And this is non-zero. Good. So now we do the same argument in the special Lorentz frame. So let's look at the right-hand side perspective, right? The second one, perspective. Okay, so we do the Lorentz transformations, and we are in the special frame where p primed is equal to the vector p primed minus p, and p is equal to p prime p plus p. But now we have twice, so we have the equation plus or minus 2I phi h of p primed t mu nu p. That now has two factors of the Lorentz matrix, lambda nu rho, lambda nu sigma, p primed t rho sigma p. The reason, of course, just being the extra Lorentz index. So this is exactly the same equation as before, but you have sort of the tensor product of the lambda factors. But on the left-hand side, nothing has changed, because I still just have p primed and its Lorentz transformation, and p and its Lorentz transformation. And of course, the fact that we look at the graviton as spin 2 object is just that this is just given by this h here. Sorry, the h just take it back. The h just is the helicity of whatever state we might want to stick in here. So this has nothing to do with graviton or anything else for the time being. It's just that whatever the h is, that corresponds to p primed and to p. But the fact that we have two lambdas here corresponds precisely to the fact that this is a 2 tensor. Well, excellent, but you can do this eigenvalue equation, and what you find now is that e to the plus or minus 2I phi h, this now has more possibilities. Now it has the possibility to be 1 as before. It has the possibility to be e to the plus or minus I phi, and it has the additional possibility to be e to the plus or minus 2I phi. Okay, this is just the solution of this eigenvalue equation, where for lambda, I choose the same lambda that I wrote here. Okay, except that now I need to act twice with it. And when I act twice with it, I add another 2 possibilities for the eigenvalue. And so therefore, the only way that this equation, we must therefore have h is either 0, h is equal to 1/2, plus or minus 1/2, or h is equal to plus or minus 1. And that's it. Right, by the way, plus or minus here, I'll write it explicitly because these signs, this sign and that sign, they are uncorrelated. They're just uncorrelated. This is the eigenvalue problem that is independent, and this is what we had here. So again, to avoid contradiction, no massless h greater than 1. Let's write it like this. In particular, no h is equal to 2, no emergent graviton. Okay, 5 minutes past the hour. Please do ask questions, of course, but I'm gonna stop here.
You mean massless in what you wrote?
Yes. Oh, yes, I mean that, and I wrote massive. It's very good, yes, 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 yes. No m is equal to 0. Thank you. Other questions? So I propose that next time in a segment, we discuss a little bit the implications. So I wanted to do it today, but I took a little bit more time. But it might be nice we start next lecture to, you know, as a reminder if you want, and we'll discuss some of the implications, which in this case are very deep. And yes, but Manos, you had a question.
Yes, similar argument in ADS or de Sitter?
And not to my knowledge, because you don't have the Lorentz covariance. But it's a very good question. So you might use instead whatever the full conformal group or something.
Yeah, all right.
it is quite yes, it's quite possible that there is some sort of constraint. And this will, I mean, this discussion, we should maybe reconsider this when we go to ADS. Of course, what we do is we actually look at flat space theories, which are dual to ADS theories. So the argument is even more involved, but it's still be interesting to try and reconsider your question. Yeah, any other questions? It doesn't look like it. So see you guys next week. Bye.
Okay, thank you. Bye.
Thank you. Bye-bye.
Bye, thanks.